In example 12.5, we are given a function definition. The name of this function is f. The equation is f of x equals x minus 1 squared plus 2, and the domain can be found here as all real numbers. What we should recognize about this equation is that it is a vertex form for a quadratic function. That means that we should be able to identify a value for a value for h, and also a value for k. Let me write h below here. H is going to be 1, and k is going to be 2. Part A asks us to graph f on the Cartesian coordinate plane. The most important point on the graph of a quadratic function is the vertex. So from the hk information, I know that the vertex will be located at 1, 2. So I'll go ahead and mark that point on the graph at 1, 2. There's my vertex. Then I look at the value of a, and the value of a is going to tell me two things. Number one, this tells me that my parabola is going to open up because that's a positive value. Second thing, because it's just 1 and not 2 or 3 or 1/2, there is no stretch or shrink. No stretch or shrink. Which means that this graph is going to look just like the parent function for quadratic. It's just got the vertex moved at 1, 2. So from the vertex, I will go over 1, up 1, go back to the vertex, and I'll go over 2, up 4. And this will give me the right half of my parabola shape. Now I know that this is the right half because one of our theorems tells us that there is an axis of symmetry that will be the vertical line that crosses through the vertex. So the left-hand side has to be the mirror image of the right-hand side, and that allows me to very quickly get the left half done and ultimately be done with the graph of f. There's your parabola shape. So that's part A. Part A was about getting the graph completed. Part B is wanting us to state the domain of f and also the range of f. So let's go ahead and do that. Part B, the domain of this function was given to us in the function definition. That's going to be all real numbers, -infinity to infinity. The range for this function is going to be the starting at the vertex, which has a y value of +2, and since the graph opens up, it'll be headed toward +infinity. It'll be unbounded in the positive direction there for the range. Part C wants us to state the intercepts for the graph. Keep in mind that when you're looking at the intercepts, you always need to think about both the x-intercepts and the y-intercepts because you could have both. In this situation, because our graph is opening up and it's already above the x-axis, there would be no x-intercepts. But there is a y-intercept that we were able to get exactly from the graph, which would be located at 0, 3. And then for part D, we are asked to state the relative extrema for this function. Remember, there's only two types of relative extrema. There is the relative minimum, and there is the relative maximum. Those are the only two types of extrema that we have. In a quadratic function, you can never have both at the same time. It's either one or the other. Clearly from the picture, we can see that the vertex represents the lowest point, which is going to be our relative minimum. So our relative minimum will be located at the vertex 1, 2, and there is no relative max. We'll write none for that. All right, moving on, part E wants us to state the intervals of increasing and decreasing behavior. The vertex is the most important point on the graph of a quadratic function. And I've mentioned that before, and I'm going to keep mentioning it because it is. The vertex is the turning point between increasing and decreasing, or vice versa. When you are looking at increasing, decreasing, remember to look at the graph from left to right. If I start on the far left, I would have to come down until I get to the vertex, and then I would go up as I continue to move off to the right. So you always want to look at it going from left to right whenever you're looking at increasing, decreasing. So the axis of symmetry is going to automatically break this up into two intervals. Everything to the left of one and then everything to the right of one. We just have to make sure that we identify them correctly. To the left of one, the graph is decreasing from negative infinity all the way to positive 1. To the right of the vertical asymptote, the graph is increasing. We would say that interval is 1 to infinity. And then lastly, the equation for the axis of symmetry of the graph of f, I will typically abbreviate that AOS, axis of symmetry, and the equation has to represent the dashed vertical line here, which has an equation of x equals 1. You can review that concept when we talked about linear functions for the first time. We talked about horizontal and vertical lines, how they are special types of linear equation. And so this one would just have the equation x equals 1. And that would complete the analysis for this function.